Welcome back. Hope you're doing well. Let's go ahead and keep working on these orthogonal sets that we've been looking at before. Namely, last time we could say if we have an orthogonal set, then the following things happen, right? These are linearly independent. If this ends up being an orthonormal basis, then this has a lot of interesting properties that remind us of things that look like Rn. But the question is when stuff like that can happen. How do we get to those vectors? How do we find a way to create an orthonormal basis? How do we find an orthogonal set out of just a random collection of vectors? The way that we could start looking at how to do this is by attempting to apply a Gram-Schmidt process to this. You may recall this from linear algebra, some other context here, where we are able to orthogonalize vectors in Rn by subtracting vector projections of that vector, getting only the orthogonal parts of them by subtracting orthogonal projections of that vector onto other subspaces. And we'll discuss a little bit more about what we mean by that as we move along. We'll talk about this in terms of Rn as well as in general contexts. The idea behind Gram-Schmidt is that when you get a collection of vectors, even if they are just a spanning set of your space, you can get them to become not only just a basis, but you can also get them to become an orthonormal basis as well. So we'll discuss this sort of construct as we start moving along and start here. But in general, our general space here is not going to be Rn. It's going to be an inner product space with an inner product and an induced norm. And we have all of our definitions from before that we have that collection of vectors form an orthogonal set whenever the inner product of any non-duplicate vectors end up equaling 0. If, in addition, the norm of each of those vectors is 1, or just the inner product of that vector with itself, then we could say those vectors are orthonormal, or form an orthonormal set. And we had a theorem from our last lecture that said any orthogonal set of non-zero vectors is linearly independent. And that's useful for us because if we have a spanning set, maybe we can get a linearly independent one and start creating some bases out of this process as well. And we'll discuss that as we go through this video. Now, an orthogonal basis is something that we want to start working with. And the question is, how can we write vectors in terms of orthogonal bases? Essentially, how can we rewrite these as linear combinations of things in terms of an orthogonal basis? Remember that if something is a basis, then I can write any x in terms of a1v1 plus a2v2 plus so on and so forth, all the way to an vn, where v1 through vn is our basis, and a1 through an are just scalars in our field. But if we have an orthogonal basis, we can have formulas for each of these elements as well. And you might notice where these constants come from in this equation below. These are coming from the formulas for vector projections in Rn. Right. These are all the vector projections of x with respect to v1, v2, all the way to vn. These are all the same formulas for vector projections. Before, we had these as dot products, x dot v1. Now we have them as inner products because we're just looking at an inner product space. This works in a general context as well. We can still find the projection of x onto v1, the projection of x onto v2. And once we create those vector projections, the sum of all of those added up together gives us the vector that we started with, the vector x. So whenever our basis is an orthogonal basis, we can solve for what these constants are. These have the same formulas as they did in terms of Rn, but replacing the dot product with an inner product. In general, if v1 through vn is an orthonormal basis, then you can take out the denominators altogether. The inner product of vi with itself is going to give you 1, so you could just write it as the inner product of x with v1 times the vector v1. Notice that these are still scalars here because the inner product yields a scalar whenever you multiply out there. So this allows us to write any vector x inside of our vector space as a linear combination of this basis. And not only that, we can get a formula for what each of the scalars need to be for that. Here's our picture again of an orthogonal projection. This time, instead of looking at it in terms of Rn, we could look at this in terms of a generic vector space. Now, the notion is this. If we have a finite dimensional subspace of V, notably, V naught here is meant to be a finite dimensional subspace here, then any vector in our vector space can be uniquely represented as the sum of two things. The sum of a projection, an orthogonal projection vector, kind of like what we had in Rn, plus another vector O, where O is going to be orthogonal to our finite dimensional subspace that we've chosen, our V naught. Again, this component P is also called the orthogonal projection of X onto the subspace V naught. Notably, a finite dimensional is neat here because you could see in our previous slides as well, whenever we had orthogonal / orthonormal bases, we have finitely many vectors. So all those had those as their particular contexts there. The reason for this is that we're not quite getting into series yet. We could get a similar formula here in this corollary for V1 through Vn if we use a series instead of a sum. But we're not going to get into series just yet. We're going to keep talking about sums here for now. So let's keep talking about finite dimensional spaces here when discussing these sorts of theorems. Now, we could go through and prove this theorem. And in fact, we're going to prove it here. And notice that this is going to be a generic way of proving this. Remember that when we did this in terms of Rn, we gave more of a picture type of proof for this rather than an actual algebraic, here's where these things are coming from type of proof. But this proof right here is going to cover the Rn case because this is a generic inner product space. And here we could be looking at any finite dimensional subspace of V. Well, if V is a finite dimensional inner product, any inner product space, any subspace of it will also be finite dimensional. So because of that, we're going to have that this will cover the case of any of the subspaces we were looking at in Rn. We can always write any vector in Rn as uniquely as a sum of a vector inside of our finite dimensional vector space, as well as by a vector that is orthogonal to that space. Now, we are saying that this representation exists, and we're also saying that it's unique. So we want to be careful about that. Where's uniqueness going to come from here? Let's say, for example, that we write X in two ways. X equals P plus O, as well as P prime plus O prime. And the question is, how are we going to be able to determine how this is unique, right? Well, if we look at this, we can start subtracting these things, and we can look at P minus P prime plus O minus O prime. Well, we know that this is X minus X. I've taken P plus O, that's X right there, and I'm subtracting P and O prime from that. Those things added together give us X. So this is X minus X. So this is the vector 0. Now, P minus P prime, P minus P prime, that's an element in our subspace, V naught. And O minus O naught is orthogonal to that. So an intuitive way of thinking of this, and this is essentially how we're going to be proving this, is that P minus P naught has to be the 0 vector. Why does it have to be the 0 vector? Well, P minus P naught is going to be an element inside of our subspace P, right? So this is going to be an element inside of our V naught space. And if O minus O naught was for some reason able to get us back to the 0 vector, well, then it would be negative V negative of that vector. It'd be negative of that vector that we chose to be that vector inside of our space V naught. Well, the negative of that vector is going to also be inside of that subspace. Well, that would mean that O minus O prime is inside of our vector, is inside of our subspace. Well, the only way that that can be inside of our subspace is if this is the 0 vector. And since negative V0 is the 0 vector, V0 has to be the 0 vector as well. Indeed, this is the way that we'll go through and proceed through the proof. We'll write X in terms of these two decompositions and observe what O minus O prime and P prime minus P end up being. It turns out that the inner product of O and O minus O prime, as well as O prime times O minus O prime, has to be equal to 0. And the reason for this is that O minus O prime is going to be something that is inside of V naught. These two things are equal to each other. And because of that, O minus O prime's inner product with itself is going to give us 0. So O minus O prime is the 0 vector. That can only leave us one choice. Since these two things are equal to each other, and then this first term is 0, that means P prime minus P is equal to 0. At the end of the day, if I try and solve now for what P and O are equal to, I get that O is equal to O prime, and P is equal to P prime. That means if I have any two decompositions, they end up being equal in both of their terms. So that gives us uniqueness. It doesn't give us existence. This tells us that there is at most one way to decompose, but we need to show that there exists at least one way as well. That will give us the exactly one way of decomposing this. But guess what? We already have one. We have one decomposition for this. We're going to take our projection of this vector. Say, let's take the vector x that we're looking at, and we're going to compose the following orthogonal projection for x. X, again, is our vector here. And when v1 through vn form an orthogonal basis for v0, we're going to take this sum right here, and we're going to add each of these things together. Essentially, we're going to create that sum of orthogonal projections to give us the vector p. Notice that this doesn't give us the vector x, because x is something outside, potentially, of this finite dimensional subspace v0. And we're only adding elements inside of v0 here. This is just the projection of the vector x into v0. In particular, this vector O, which is x minus p, might very well be non-zero. It might have another component to it. Well, by construction, x is equal to p plus O, and p is going to be inside of our vector space, since it is a linear combination of basis elements for that vector space. Well, just like in our previous lecture, we're going to get that p comma v sub I is equal to x comma v sub I, and that is since any component of this vector x that is outside of our vector space v0, our subspace there, is going to evaluate to be 0. So that is going to give us that these things are all equal to each other right here. Well, then what is that going to mean? That's going to mean that in respect to each of those vi components, and if I take a look and see what happens with O in terms of that, well, we know that x times vi is going to be equal to, since x is p plus O, we're going to get that that is p vi plus O vi. And that's because of this decomposition right here. Well, if this is equal to x comma vi, this is the same as x comma vi, well, then I'm only left with one option. This has to be equal to 0. That means, indeed, that O is perpendicular or orthogonal to each vector v sub I. And since that's true for all vectors that span v0, we know that O is orthogonal to v0 as well. This concludes what we need to do, because we've shown that p is inside of v0, where p is this vector here, and O is orthogonal to v0, where O is the subtraction of x minus p. So this gives us a proof for this in a generic inner product space, but we could have now plug in v is equal to Rn, and v0 is any subspace of Rn. Now we have the proof in a specific case of Rn, but we have it in more than just Rn now. We have it in functional vector spaces as well. Of course, whenever we're in functional vector spaces, we have to keep in mind that this works for finite dimensional subspaces here. At least this formula does. Let's do some Gram-Schmidt. Gram-Schmidt is the thing that's going to allow us to take any collection of vectors, say we start with a basis for v, and turn it into the orthogonal basis. Notably, we needed an orthogonal basis for the proof of existence here in the previous theorem. So we want to ask, okay, how do we form an orthogonal basis out of just a generic basis? We know from our previous lecture that any vector space has a basis, so how do we turn that into a more specific one? Now, for this one, we're going to stick with finite dimensional bases again. So that's what we're going to do here. And the reason for that, again, is that we want to get out of the idea where you have to do this infinitely many times. So we're going to look at just finite dimensional vectors here. The way we're going to make this orthogonal is this. We're going to take v1 to just be x1. Let's let v1 through vn be our soon-to-be-shown orthogonal basis for this vector space. And of course, x1 through xn are still our generic basis here. Now, here's the deal. I could write x2, v2 equals x2, but I might already have lost orthogonality, because x1 and x2's inner product does not have to be, this inner product right here, does not necessarily have to be equal to 0. This is not necessarily true. But if I subtract the vector projection of the vector x2 from the vector v1, what happens? Right? So what happens here? So here's the picture. We've got that v1 is equal to x1. So we've got this guy right here. And x2 might be going off in, say, this direction. v2 might be going off in this direction. We might take the inner product of these two vectors and realize, oh wait, this inner product here is not equal to 0. So here's what I'm going to do instead. I'm going to take the projection of x2 onto v1, v1 being x1, because those two things are equal here. I'm going to take that projection right here. And now, instead of making v2 equal to x2, this vector right here, I'm going to take v2 and I'm going to subtract away its orthogonal projection. So what I'm going to get is this guy right here. Well, this is already orthogonal to the vector v1, so this will continue our process of making an orthogonal basis. v1 and v2 should now be orthogonal to each other. And we're going to continue this process for v3. v3 does not have to be orthogonal to either v1 or v2, but we could subtract away its orthogonal projections from each one. We can subtract away v3 as orthogonal projection from each one. Notice, by the way, that as we do this, we never get that v3 is equal to the 0 vector. Well, why not? Why is v3 never equal to the 0 vector here? If it were, then we would be able to write x3 as a linear combination of elements of scalars, and a linear combination of v1 and v2, which are themselves just linear combinations of x1 and x2. So that would mean that x3 is not linearly independent from x1 and x2 and would resolve in a contradiction. So we know that v3 is going to be a non-zero vector here, thanks to the fact that v1 and v2 are linear combinations of x1 and x2. And if this were equal to 0, we would be able to write the equation x3 equals the sum of these two things. Right? I'm not going to complete that equation. The reason is that we know specifically that that's not true, that this is not equal to 0. So I don't want that to be confusing. We can continue this process all the way through, no matter how many dimensions that we have. This is just for the first three vectors, but there's a pattern that's established here. If I wanted to find v4, I would take x4 and then subtract away specific scalar away from v1, one from v2, and one from v3. Once I do that in general for each of the other vectors here, then v1 through vn, we have shown kind of inductively here that v3 is orthogonal to v1 and v2. v4 we would be able to show is going to be, orthogonal to v1, v2, and v3. And so all the way down, we would have shown orthogonality between any pair of these two vectors. Hence, v1 through vn would be an orthogonal basis for our vector space. Okay. So here is that picture of what we're looking at. So let's say that we're taking a look at this vector subspace down here, which is the span of the first two vectors, x1 and x2, or v1 and v2. These spans are exactly the same thing. You may notice in the formulas for that, x1 is just v1, and x2 is a linear combination of x1 and v1. And v2, rather, is a linear combination of x1 and x2. So because of that sort of way of writing the formula, we know that these two spans should be the same. They both include each other's vectors. So these two are each the same subspace. Now let's see what happens when I add v3. When I add a vector like x3, I should say, a vector x3 to this collection, I notice that x3 may not necessarily be equal to or have an orthogonal relationship with each of the other two vectors, v1 and v2. So what we have to do is fix that. What we do is we find the orthogonal projection for that vector. We find the orthogonal projection. And the way we find that orthogonal projection is with this formula. x3 is the thing that we have inside of each of here, and v1 and v2, respectively, these are the two vectors that generate this subspace. So when we write p3, this is the formula that we get for the orthogonal projection here. Finally, what do we do to write v3? We take x3 minus p3. So this is going to give us v3 here. And indeed, that's exactly the formula that we have right here. So this is the notion of Gram-Schmidt orthogonalization. Now, a lot of neat things happen with Gram-Schmidt, and we'll talk about some of those properties here. We'll keep the same notation as before. We can take any basis now we know and turn it from x1 through xn to v1 through vn, where x1 through xn is not necessarily orthogonal, but v1 through vn absolutely is. Let's talk about each of the properties here. First, vk is going to be written in the following form. It's going to be xk minus a linear combination of things in terms of x1 through x sub k minus 1. What this is saying is that each vector v sub k is in the linear span of the x1 through xk vectors. And you don't have to go past xk. You don't have to look at x sub k plus 1. V sub k is only in the linear span of the x vectors that came before it in index, including xk itself. We don't know quite what these scalars are, because remember that when we define the Gram-Schmidt process, this isn't x1 right here. This is v1. This isn't xk sub minus 1. This is v sub k minus 1. So that's how that looks like in the actual Gram-Schmidt process. So we don't quite know what these scalars are. But we do get that v sub k is in the linear span of x sub 1 through x sub k. In fact, we can now see that the span of v1 through vk is the same as x sub 1 through x sub k. And that comes from the fact that v sub 1 and v sub k are orthogonal and hence linearly independent. And since they do not extend the span of x sub 1 through x sub k, they are themselves a subspace inside of x sub 1 through x sub k with the same number of generating linearly independent vectors. And hence, they must generate the same subspace. We also know that v sub k is orthogonal to each of x sub 1 and x sub k minus 1. So it's orthogonal to each of these. And the reason is that it's any elements inside of x1 through x sub k minus 1 is in the span of each of the v sub 1 through v sub k minus 1 that came before it. And we know that v sub k is orthogonal to each of these. And so hence it is orthogonal to the span of those. And hence will be orthogonal to all of the other x coordinates that are given there. Notably, v sub k is not necessarily orthogonal to x sub k. In fact, that is rarely the case. And the fact that turns not only to be the case when we don't have a basis to begin with. As you can see right here, v sub 3 and x sub 3 do not have to be orthogonal to each other. So it's only with the ones that come before it in index. And then finally, just like we saw in that formula from before, v sub k is x sub k minus p sub k, where p sub k is the orthogonal projection of this vector onto the subspace spanned by the previous vectors x sub 1 through x sub k minus 1. So this is the same, this is the orthogonal projection that is helping us calculate these things out. Now, how do we normalize this? Well, the answer is that this is the neat part. This is the neat, easy, dust your hand off. It's nice and easy, nice, tidy, well and done. If we have an orthogonal basis, all we have to do is just divide by their lengths. Orthogonal is the tricky part because that's Gram-Schmidt. But then after we get all of those vector elements, we just have to say, okay, what's the length of those vectors? If it's not 1, divide by the length. We know that these are non-zero, so we're not dividing by 0 when we do this, and hence this gives us an orthonormal basis for our vector. So now we've seen, thanks to the fact that for any basis, we can Gram-Schmidt to get us to an orthogonal basis, and then divide by their lengths to get into an orthonormal basis. We've proven this theorem. Any finite dimensional vector space with an inner product has an orthonormal basis. Okay, quick remark here. An infinite dimensional vector space with an inner product may or may not have an orthonormal basis. So it's going to be interesting trying to work with some infinite dimensional vector spaces. Sometimes we are going to have orthonormal bases. We can do all of this process, and sometimes we're just not going to be able to do that. There's going to be a difference between these types of vector spaces that are infinite dimensional that end up having an orthonormal basis and that don't. And we can say that any vector space that is complete with respect to its inner product, complete meaning that its Cauchy sequences converge, and we'll talk about some of these definitions as we go into the second half of this course. Those have orthonormal bases. We call those things Hilbert spaces, by the way. That might be a name that comes up depending on your research later on, especially if it goes into more of, say, of an applied or analytical realm. You might see it go off into those directions. But Hilbert spaces all have orthonormal bases. Infinite dimensional vector spaces in general don't necessarily. They don't necessarily have that. Let's see how this can be useful for some problems. Let's see if we can generate some Gram-Schmidt orthonormal bases based off of the processes and the algorithms that we've been looking at already. Let's let pi be the plane. This is a capital pi here. Let's let this be the plane spanned by x1 being 1, 1, 0, and x2 being 0, 0, 1. And let's start by trying to find the orthogonal projection of the vector 4, 0, negative 1 onto the plane of pi. Then we'll go through and try and find the distance. We know orthogonal projections of this are going to help us find the distance because we have the same content of what we had from our previous class, our previous lecture on Rn applying here. We can define the notion of distance to be the distance of the vector O, which is x minus p, whenever we write that decomposition of x equals p minus O. And that's exactly what we're going to essentially do here. But in order to find this orthogonal projection, we need to first figure out what that formula is going to be. Well, that formula is going to be given by looking at the Gram-Schmidt process. We're going to start by looking at V1 and V2. We need that in order to find that orthogonal projection. So we're going to apply that to this plane. Right now, we notice that 1, 1, 0 and 0, 1, 1, at least in terms of the R3 inner product, they aren't already going to be orthogonal to each other. So we need to apply Gram-Schmidt in order to make this happen. So we'll make V1 equal to x1, that's 1, 1, 0. And then we'll make V2 equal to x2 minus the orthogonal projection of x2 onto V1. And we'll go through and compute what these values are. For example, the inner product here is going to give me 1. The inner product of V1 with itself is going to give me 2. So that gives me this constant 1/2 times the vector 1, 1, 0. Once I do that, I get the vector negative 1/2, 1/2, and 1. Now V1 and V2 is an orthogonal basis, so I can use my formula for an orthogonal projection. V1 and V2 now form an orthogonal basis, so I can go back up to the previous work that we've been doing and find this value, this function, this vector P that we're looking for here. So we take the vector y, 4, 0, negative 1, and take its inner product and plug that in here for this formula to find what V1 it is for the V1 component plus adding it to the V2 component. We do a little bit of math here to try and figure this out. Namely, the inner product of V1 with itself is still 2, so we see that here. The inner product of y with V1 is going to give us just 4 times 0, or 4 plus 0 plus 0, so that's going to give us 4 over 2. And then we can do the same for each of these other numbers as well for the V2 component to give us 3 divided by 3/2. When divided, that should give us negative 2. So when we multiply that out to the vector V2, which we said was negative 1/2, 1/2, and 1, that should give us 1, negative 1, negative 2. Then going back to the first vector, we have 4 over 2, which is 2, times 1, 1, 0 gives us 2, 2, 0. Adding those together gives us the orthogonal projection of y onto pi. Now, what's the formula for that distance? That's right. It is the length of y minus p. And that's just going to be applying a distance formula to 1, negative 1, 1. That is the difference between this value for y and this value for p. All right, so that's kind of the math behind how we are using this to find orthogonal projections as well as distances from a point to a plane. Finding and having the Gram-Schmidt orthogonal basis for this is kind of what set us over the edge here, because it allowed us to, instead of having to just kind of do one orthogonal projection onto a vector, it allowed us to do it for however many vectors span our plane. We could have done this for 3 vectors or 4 vectors by continuing on with the Gram-Schmidt process, but we only needed to do it for 2 vectors because it was just a 2-dimensional vector space. Now, this one's a little bit different. Let's take the subspace that is spanned by 3 vectors. This time, 1, negative 1, 1, negative 1 being one of those vectors. This one being a vector in R4. x2 being 1, 1, 3, negative 1, and x3 being negative 3, 7, 1, and 3. So first thing we're going to do is apply this Gram-Schmidt process to these vectors and attempt to attain an orthogonal basis, V1 through V3, for the subspace V. After that, we're going to go ahead and compute the orthogonal projection for this of y onto V. Then finally, the distance from y to V is going to be y minus p. That's going to be the length of the vector O. Alternatively, we have another option here. We could have gone through and instead say, okay, let's do this. Let's take the Gram-Schmidt process and have it applied to the vectors. Instead of everything else, let's do x1 through x3, and then let's add in y as well. And the reason is that y, once I go through and apply the Gram-Schmidt process to it as well, we're going to find the component of y that is orthogonal to each of all the other vectors. Well, guess what? That leftover orthogonal vector is exactly the length of, taking the length of that is going to give us exactly the distance that we're looking for, because that's the vector O. When you orthogonalize it, you're going to get the vector O. That comes back to this picture right up here. When I orthogonalize the next vector in the sequence, I get one that's orthogonal to all the other ones, and that's going to give me my distance that I'm looking for in between these 2 vectors. So we could apply either one of those 2 processes. I think this one We're going to start by just working with x1 through x3 and kind of see how it goes on from there. So let's start through and take a look at what x1 is. Well, x1 is just going to be the vector itself. We don't have to orthogonalize in any way. Then let's take x2, or find what v2 is in terms of x2 and x1. We use the Gram-Schmidt orthogonalization to go through and do this. Calculating what these inner products are, we can calculate quickly that the dot product here should indeed be 4 in the numerator, as well as should be the inner product of v1 with itself, the inner product of taking components and multiplying should just give us 1 in each component. So that should give us -4/4 in this part right here to give us this vector for v2. And then we can keep going to find the orthogonal projection or the orthogonal component for x3 in terms of v1 and v2. So we subtract away the orthogonal projection of x3 in terms of v1 and v2. So we calculate what those inner products are going to be, do some math on that. And what we end up with is interesting. We get the vector 0. We get the vector 0 from this. What does this mean? Remember that this right here, this is the projection. This is the orthogonal projection. Orthogonal, got to spell it right. Orthogonal projection of x3 onto the span of v1 and v2. So what does it mean that this vector is 0? We took x3, we subtracted away the orthogonal projection of x3 onto the span of v1 and v2, and we got 0. That means that these two things are equal. If we project x3 onto the span of v1 through v2, we go nowhere. We just get the same vector back. What does that mean? That means that x3 was already in the span of v1 and v2 to begin with. But wait, John, I thought that that could only happen whenever x3 was not linearly independent. Take a look at this problem. Doesn't say that x3 is linearly independent from x1 and x2. That's something to keep in mind. This x3 can be written as a linear combination of x1 and x2 here. And we actually found that as part of the Gram-Schmidt process, namely x3 is equal to its orthogonal projection into span v1 and v2, namely x3 is inside of here as a result. So the Gram-Schmidt process can be used to check linear independence of vectors as well. The only reason that we got 0 here for v3, we use the word failed in quotes because really it kind of succeeded in a way. It told us that x3 is a linear combination of x1 and x2. That means that v is a plane, not a three-dimensional subspace. So why don't we just go ahead and drop x3? We don't need x3 anymore. We already have what v is spanned in terms of, and that's going to be v1 and v2. So we don't even need to worry about x3. We're just going to continue on and talk about y instead. So we're going to call v tilde 3 our projection or our orthogonal component of y when it's orthogonal to the span of the vectors v1 and v2. So now, instead of taking the span of v1, v2, and v3, like we would expect to do at this step, since v3 is extraneous, we're going to throw it out. And we're just going to see the orthogonal component of y with respect to its span of v1 and v2. So we go through and do the math on this, same sort of inner products as before, and that gets us the vector 1/4, -1/4, 1/4, 3/4. And if we go through and find what this magnitude is going to be, we're going to get the square root of 12/4, or square root of 3/2. So this Gram-Schmidt process can be used to help us check linear independence of these vectors as well. If we ever get that, for example, like we saw up there, that v3 gives us 0 after taking x3 and subtracting its projection onto the span of x1 and x2, then what we figure out is that x3 was not outside that span to begin with. It was already a linear combination of the other two vectors. Because of this, we can just throw v3 out and we can continue on looking at just v1 and v2. Right. So we've worked through now an example here with R3 and an example with R4. But remember that we have this whole operation of Gram-Schmidt for more than just R3 and R4. We have these in terms of any inner product space, an abstract inner product space, even functional inner product spaces. So why don't we go ahead and take a look at that here? Why don't we see if we can use the inner product of the continuous functions going from 0 to pi and use this inner product of the two functions here being the integral of the product of those two functions going from 0 to pi to construct an orthonormal basis for the set 1 sine x and sine squared x. So we're going to be taking a few steps here. Remember that in order to take this element 1 sine x sine squared of x, we're going to start by taking these functions, and then we're going to take these functions and start making them orthogonal, and then we're going to make them orthonormal. So let's go ahead and call them like this. Let's say f1 of x is 1, f2 of x is sine x, and f3 of x is, f3x is sine squared x. And let's write them to be h1 of x, h2 of x, h3 of x, such that these sets are, or these functions are orthogonal. And then once we're done with that, we're going to be taking each of these functions, h1, h2, and h3, and in order to make them orthonormal, we're going to be dividing them by their norms. We're going to be dividing by h1 norm, dividing by h2 norm, and dividing by h3 norm. So why don't we check that out here and see how this Gram-Schmidt orthogonalization is going to be working with this set, okay? So first things first, h1 is going to be equal to f1. No need to change anything there. We're just going to make h1 equal to the function 1. Now let's take a look at f2, okay? h2 is going to be, well, f2 minus something else. It's going to be taking f2 and subtracting away something. What is it subtracting away? Well, we know that this is going to be the inner product of f2 with h1 divided by the inner product of h1 with itself. So this is that projection onto the function h1 times h1. So there is that projection here. Now, how are we going to calculate each of those things? Well, f2 is sine of x, so we can just plug that in. Minus f2 times h1, or at least the inner product of those two things. What is that going to be? That's going to give me the integral of sine of x times 1. So that's just the integral of sine of x. Hopefully not too bad. So we go through and integrate 0 to pi of sine of x dx up here. And then we divide that by what? We're going to be dividing that by the integral from 0 to pi of, what is h1? It's just the function 1. So we're going to be integrating that of 1 times 1 dx. So what are we going to get after we multiply these two together? And of course, multiply those times h1, which is just 1. What we should get is the function. Integral of sine of x is negative cosine of x. Evaluating that from 0 to pi should give me something like, 2? So we should get sine of x minus 2 over the integral of 1 dx is just x. Evaluating that from 0 to pi should just give us pi times 1. So this ends up being the function sine x minus 2 over pi. Think of the 2 over pi here as something being subtracted from sine of x in order to make it orthogonal to the function 1. We had to subtract the orthogonal projection of the function 1, of the function sine of x from the subspace generated by the function 1. Notice that 2 over pi is indeed a linear combination of the function 1, just a scalar multiple of it, because 2 over pi is a constant. So we are subtracting away that orthogonal projection there when we write that. And then we do the same process this time for h3. So we're going to start with f3. That's going to be this guy right there. Minus, we'll do f3 and its orthogonal projection onto h1 and write out what this one is. Minus f3 and how it works with h2. We'll divide that out here with h2 as well. Okay. So let's take a look at what this formula should be. Okay. Well, we can start by, I'm just kind of looking at my notes over there. That's what that little aside was for. Well, we can write this like this. f3 we know is sine squared x. Minus, we could go through and integrate. Well, if we're just integrating this one, we could just do integral of sine squared of x dx. This one going from 0 to pi. We know, again, that we could write this one in terms of a double angle formula. Divided by the integral of 1, 0 to pi. And we've already done this one, so we could actually erase this and say that this is just pi, because we've already calculated what this is. Minus, we can now go through and integrate f3 times h2. That's going to be the integral of what? Something like maybe the integral from 0 to pi of, we have sine squared of x, and we want to multiply it times this on the inside. So we're going to get sine cubed of x minus 2 pi sine squared x. And then what we're going to do is we're going to divide that here by the let's see, the integral of from going from 0 to pi of h2 and h2. So that's going to be sine x minus 2 pi times sine x minus 2 over pi. So that's going to give us this value right here. And then finally, we multiply that times h2, which is sine x minus 2 pi. Okay, so let me check something here, because I like working at this a little bit. Okay, looks good, looks good. Okay, so this is our formula for h3. Now, this is a lot of math. Look at all this math that we've kind of made here and created for ourselves. This is still using the Gram-Schmidt orthogonalization, but each of these, once we factor everything out and integrate, ends up being kind of its own little integral. Now, there's a lot of things that are in common here. Right? Integrating sine squared here as well as here. And once we find all of these values here for integrals, all these are just going to be as constants. Could be strange constants, but they're all still constants. So they're all going to be linear multiples, linear combinations of these functions that we have here. Of course, being the function 1, I should write that real quick. And that's going to give us our value of h3. Once we go through and find the norm of h3, we can just integrate, we can just evaluate that. Right? h2, for example, I will be finding the length of h2 by calculating this right here. If I calculate the integral from 0 to pi of this value, then what I'm doing is I'm finding h2, h2. And remember that if I take the square root of that, then what I get is the length of h2. So I'm already doing my work to find orthonormal by finding this Gram-Schmidt process. I just have to, once all of this is done, eventually, I'm going to have to divide by the length of h2. And that's what I'll have to do to get this value right here. So this is the work that it takes to figure out an orthogonal and eventually an orthonormal basis for this subspace. So let's see this work in one more example. Let's take a look on this subspace here, the span of 1 sine of x sine squared of x that we were looking back up here from this previous example we've been working on. And let's find the orthogonal projection of this function, cosine to the 4th of x, onto the span of these vectors here. Now, how are we going to find an orthogonal projection in an abstract vector space? Well, the way that we're going to do it is we're going to use the formulas that we were looking at before for finding the vector p. P is going to be we're going to start by looking at f as our function, and we're going to be writing it in terms of the inner product of f with our first vector, h1. By the way, this is h1, not f1. h1 being the function that we got up above here in orthogonalizing this basis, this 1 sine x sine squared of x. So these are these functions right here rather than these functions, because if we just use f1, f2, and f3, we would not be looking at something orthogonal to begin with. We wouldn't be getting us in the right direction. Our elements would not necessarily be the orthogonal projection because it does not have the correct formula for it. So we would be using this orthogonal basis to be doing this, the inner product of f with h1 to start off and getting that projection for h1 taken care of. And then we would add this to each of the other formulas. This time, instead of h1, we'd be looking at plugging in h2 for each of these functions. And then finally, we would do it for the last basis element here. We do this for h3. This would be the formula for this. So for example, this top one right here, this top inner product would look a little bit like this. You'd be integrating f times h1. That's cosine to the 4th of x times h1. Well, h1 is just going to be 1 right there. All right, so you could just use that there. Now, I would also have to be dividing by the inner product of h1 with itself. And that makes sense. That's something that I'm going to have to go through and do. But I could also have done something else. Because in that process of what I was doing up in the previous problem, instead of working with the orthogonal basis h1, I could have been working with h1 prime. Let's say that we go through this and find this orthonormal basis, h1, h2, and h3, each divided by their own lengths. And let's name h1 hat, the orthonormal basis element that is granted from taking our orthogonal basis element h1 and dividing by its length. Same thing for h2 hat and h3 hat. Then we could write P in a different way. We could write this as just, instead of having to evaluate 6 integrals, or rather having to divide some rather interesting things from our previous integrals from before, we can now just go through and evaluate this formula, the one that we had for an orthonormal basis, which looks like something like this. So here we get to replace each of h1, h2, h3 with h1, h1 hat, h2 hat, and h3 hat respectively, and we get to say, well, we already know what each of these guys are. Each of these inner products is 1, so we get to remove those entirely. And all that we have left was h1 hat, h2 hat, and h3 hat as our linear combination elements to work through here. So now, for example, this ends up looking like this. You're integrating the f, which is cosine to the 4th of x, times, well, h1 hat. Remember that h1 is the function 1, but 1 had a length of, we calculated this, the length of h1 was the square root of the integral from 0 to pi of 1 dx, because this is the inner product of h1 with itself. That value, remember, was pi, so we would have to divide by the square root of pi. So again, we've noticed here that this is h1, h1, and then if we took the square root of h1, h1, then we would get the magnitude of h1 hat. So because this value is pi, as seen right here, we know that this function would be times 1 over the square root of pi whenever we go through and integrate this. And now we'd be multiplying that times h1 hat, which is the function 1 over the square root of pi. So in fact, we'd actually end up dividing by pi, which is the same thing that we'd be doing if we were working in the previous format as well. So that kind of also shows us term by term that this is the right formula for calculating this orthogonal projection. But now we see the math behind it, and the rest of it turns out to be a good bit of integral algebra. But that does it for us here. That helps us get an idea of how to apply the Gram-Schmidt orthogonalization algorithm to any basis, turn it into an orthogonal basis, or even, as we've seen, a spanning set, not necessarily a basis, or just something that spans a subspace. And that's because we can just, the orthogonalization process ends up plucking out specific vectors that are already linearly dependent by getting us 0 for those vectors whenever we subtract the orthogonal projections onto the span of the vectors that came before it. But that will do it for us today. Thank you so much. Have a wonderful day.